Alright, let's look at the example. So we're going to apply the plus-minus theorem to answer the following questions. The first one, is S linearly independent in R3? So S is given by that set of three vectors, and we're asked to use the plus-minus theorem to determine the answer to this question. Normally you would set up your equation in the normal way, and then to determine linear independence you need to find the trivial solution for the case. However, we're going to use a slightly easier way of proving this using the plus-minus theorem. Right, so let's see what happens. Alright, so let's take the set S prime of the two vectors, 1, minus 2, 0, and minus 7, 1, 0. And we claim that S prime is linearly independent. Okay. Right, so how do we prove that? Right, so we take two real numbers k1 and k2 such that k1 times vector 1 minus 2 0 plus k2 times vector minus 7 1 0 is the 0 vector. And from that we can set up a system of equations which will be the following. Right, so there's our system. That's the first equation. And the second one. Alright, and from that it follows that. Okay, so we have that k2 is 2 times k1, and substituting that into the first equation we get. Right, so we can from that then solve for k1 and k2 as. Right, so from there we get that k1 is equal to k2 is equal to 0. So those vectors are linearly independent. Alright, so what does the plus-minus theorem, what does it basically say again? Look at the first point in the plus-minus theorem. Right, so we said there that if S is a linearly independent set, and if V is a vector that lies outside of the span of S, then putting V back in S is still going to be a linearly independent set. Alright, so what we need to ask the following question. The question is this vector that we have, is it in the span? Is it in the span of the set S prime? Is it in the span of the S prime? And how do we determine whether it's in the span or not? For it to be in the span, 0, 0, 1 needs to be a linear combination of when is it in the span of S prime? It needs to be a linear combination of the vectors in S prime. So let's see if this is the case. So let's take two real numbers, and let's see if it can be expressed as a linear combination of vectors in S prime. So we set up this equation. So we take the vector, and let's say it's expressible as that linear combination. Can we find values for k1 and k2? That's now the question. Right, so we take that information there and see if we can find those scalars. Right, so from there, basically, it follows that you can set up those equations again. 0 is k1 minus 7k2. Okay, and the other equation is 0 is equal to minus 2k1 plus k2. Okay, and then from there it follows that k2 is 2k1, and then you plug it into your first equation, which then gives this information here. and from there it follows that K1 is equal to K2 is equal to 0. Okay, so now if you go back to your original equation here, if you make K1 0 and you make K2 0, on the right hand side you've got the 0 vector, and on the left hand side you've got the one of the standard unit vectors, and surely this is not possible. Okay, so that's not possible. So what does that imply? It implies that definitely 0, 0, 1 can definitely not be in the span of S prime. Cannot be in the span of S prime. Okay, so let's apply the first part of the plus-minus theorem. Okay, the first part of the plus-minus theorem says that if you take a linearly independent set and you take a vector that doesn't lie in the span of that linearly independent set, then throwing that vector back into the set is still going to be a linearly independent set. Alright, so you can say that by the plus-minus theorem, the linearly independent set S prime, which we said were those two vectors, union with the vector 0, 0, 1 is linearly independent. All right. Okay, so we know that S is basically S prime union this vector. Okay, we know that that is, okay, so that is, that's the first problem. Alright, let's look at the second one. There we are asked to find the span of that set in P3. What is P3 again? It's all polynomials of degree at most 3. So we want to find the span of that. We can apply the second part of the plus-minus theorem, so which says that if V is a vector in S, and this vector in S is expressible as a linear combination of all the other members of S, then we can just remove this vector from S, and the span of the original set S is still going to be the span of the set that I have removed that vector of. So it's not going to influence the span if I throw that vector away. Alright, so let's take my set S, and we need to find the span of that set. So the first thing I want you to observe is that we can express this vector 1 plus x. We can express it as a linear combination of all the other vectors in S. So you can express it as 1 times 1, okay, plus 0 times 2 minus x. Okay, right, then also plus 0 times the other vector, which is minus 2 plus 4x. Right, plus 1 times x. Alright, so it's a linear combination. So you can see it's a linear combination of those vectors. Okay, there we go. So that is that. Those vectors there. Okay. So the plus minus theorem says I can remove 1 plus x without influencing the span. Alright, so the span of S is therefore the span of S minus that vector that I've shown to be a linear combination of all the other vectors. So can we still continue with removing vectors? The answer is yes. Alright, so let's take our set S without the vector 1 plus x, which is the set there on the right hand side. And can I do any further subtractions there? Let's see. Right, so yes, the answer is yes. I can express this function here, or that polynomial there. I can express it as minus 1 times that function there, plus 0 times that function there, plus 3 times that function there. So this is a linear combination of that vector, and that vector. Okay, so by the plus minus theorem I can go and remove that vector to form a new set. Right, so therefore, by the plus minus theorem, the span of S minus 1 plus x is the same as the span of S minus 1 plus x, 2 minus x. Okay, is that it now? Can we remove any further functions? Okay, so let's go and see if what happens now. So take that information there and continue. Alright, so let's look at the following linear combination. Right, so look at that linear combination. Alright, now don't forget that this set here is the set 1 minus 2 plus 4x. Alright, and don't forget the this linear combination. First term is minus 2 times the first vector, which is 1. Second term is 4 times x, which is the third vector in my set. Okay, so by the plus minus theorem we can again go and remove a vector. So therefore the span of S minus 1 plus x, 2 minus x is basically equal to that term there. It's equal to the span of S minus 1 plus x2 minus x minus 2 plus 4x. Right, and that is basically the same as the span of this set. So the only two remaining vectors is the vector 1 and x. Now the question is, can I express x as a linear combination of 1 or 1 as a linear combination of x? And the answer is no. So that's as far as I can go. Can't remove any further vectors. So what is the span of S then? The span of S is the following. Right, so the span of S is just the span of the set consisting of 1 and x. Okay, and therefore what is that? The span of 1 and x is pretty much, it's all polynomials of the form c1 plus c2 x, where c1 and c2 are basically real numbers. So that is what the span of S looks like using the plus minus theorem. Okay, that brings us to the next theorem, Theorem 4, Theorem 4.5.4. This theorem states that if V is an n-dimensional vector space and S is a set in V with exactly n vectors, then S is a basis for V if and only if S spans V or S is linearly independent. Now take note of this or. Or, it's weaker than and. For us to check both linearly independence and the span property, to check them both, we're checking the span and the linearly independence. That's much more work to check both. Whereas or, we only have to check one or the other. We don't have to check both. So this is an interesting property of a finite dimensional vector space. What it says is that I don't have to check both properties. It's enough for me to check one property. Because if one of the properties hold, immediately both properties are going to hold. So that's what we need to prove. So why is it with a finite dimensional vector space, I only have to prove one of the properties? Why is it not the case that I have to prove both? And the answer to that is we're going to quickly look at that. All right, so we're first going to take a set S of n vectors. And then we're going to play around with that set and see what happens. All right, so let's assume first we start off with our set with n vectors. And let's assume S is a basis for V. Well, then obviously S is going to span V and S is going to be linearly independent. Okay. So we've proved the one part of the theorem, okay, which is this part, the part that goes from left to right. So if we go back here, so assuming S is a basis for V, then we need to prove that either S spans V or S is linearly independent. Well, if it is a basis, then obviously it's going to span V and it's going to span linearly independent. So therefore it's going to either span V or be linearly independent. So it's going to satisfy that property. So now what we're going to do is we're going to assume that firstly, let's look at the case where S spans V, and then we have to show that it's a basis, okay? And we have to show that if it's linearly independent, happens to be linearly independent, then it's also a basis for V. Right, so that's what we're going to do now. All right, so let's first assume that S is linearly independent. Right, now if S spans V, then S is a basis. Then we are finished, right? So we need to look at the case where S doesn't span V, right? So what does it mean? So if S doesn't span V, then it means that there's a vector in V that does not lie in the span of S. In other words, V is not a linear combination of vectors in S. We know by the plus-minus theorem. We know that if you have a set of vectors and there's a vector that lies outside of the span of that set of vectors, then I can throw the vector into the set without influencing the linear independence. All right? Okay, so recall now that we said S is linearly independent, and we want to show that S is a basis. So let's say it isn't a basis, so therefore S doesn't span V, and so there's a vector in V that lies outside of the span of S. Now, the plus-minus theorem says that if you have a linearly independent set and there's a vector outside of the span of that set, I can go and throw that vector V into the set S, and I can still get a linearly independent set. So I get a contradiction. Why do I get a contradiction? Well, what is the problem with this set here? That's the question. What is that? Why can that set not be linearly independent? Okay, so what is the problem with that? Now, by previous theorem, if in an n-dimensional vector space, no set with more than n vectors can be linearly independent. Right, so recall that from the previous theorem. So recall that a set with more than n vectors cannot be linearly independent. Okay, but how many vectors does the set S union V have? S union V, S has got n vectors, and V, adding V to the set S, it will have more than n vectors. Okay, so we're saying that this set here is linearly independent, but it's got more than n vectors, which is impossible. Right. Okay, so now we assume that S spans V. And is it enough for S to span V for S to be a basis? Well, we need to check that if S spans V, then S will also be linearly independent. All right, so let's assume S is not linearly independent. Now, what does it mean for S to not be linearly independent? It means that we can express one vector in S as a linear combination of all the other vectors in S. So this is equivalent to just saying that, well, there's a vector V in S that's a linear combination of all the other vectors in S. So it means that V is in the span of S minus V. So V is a linear combination of all the vectors in S minus V. Right, so by the plus-minus theorem, what do we know? By the plus-minus theorem, the span of S is going to be the same as the span of S minus V. Right. But S minus V has got how many vectors in it? It's got n minus 1 vectors. So, right, so what does that mean? Remember we said that S spans V, right? So it also means that S minus V also spans V, because the span of these two sets are the same. The span of these two sets are the same. So therefore S minus V spans V as well. But what's the contradiction? We said earlier there's a theorem that said that if you've got fewer than n vectors, a set of fewer than n vectors, it cannot span the whole space V. It's impossible. That gives us a contradiction. So therefore, we can assume that S is linearly independent. Okay, so let's look at apply this theorem. So they ask us, is S a basis for R3? Now remember, in the previous examples we did, we proved that that set S is linearly independent. Remember, we used the plus-minus theorem. We first took this a set of two vectors. We showed it's linearly independent. And we showed that this vector lies outside of the span of those two vectors. So the plus-minus theorem says we can add the vectors, that vector to the two other vectors and form a linearly independent set. Now, in the case of finite dimensional vector space, it's enough to only show one of the two properties for a basis, to have a basis. So that set S is linearly independent. So by theorem 4, it will be a basis because it is linearly independent. So I don't need to show that it spans the whole set of V. I can just show that it is linearly independent, which it already is. Okay, so theorem 5 says that if S is a finite set of vectors in a finite dimensional vector space, and you take the set S and the set S happens to span V, then we can create a basis as follows. If S is not a basis yet, then it means it's not a linearly independent set. So there are vectors that are linear combinations of the other vectors in S. So I can just keep removing these bad vectors from S until I get a linearly independent set. And I will not influence the span of the set S by removing these vectors. Alright, so then if I take the set S and it happens to be linearly independent but not a basis yet, then it means that S won't span the whole set of V. And so there are vectors that lie outside of the span of V. The plus minus theorem says I can keep adding these vectors without compromising the linearly independence. So I can just keep adding vectors to the set S until I span the whole set V, and it will still be linearly independent, so I can form a basis that way. Alright, so this example here, find basis for the respective spaces using the elements of S. So let's look at number 1. We take the set S given by those polynomials in P2. I need to find a basis. Now remember, what's the dimension of P2? So if we look at the standard basis for P2, there are 3 vectors in the standard basis. So this P2 is three-dimensional. So we have the number of vectors in the basis now, and now we can obviously S has got 4 vectors in, so we're going to have to remove vectors. And we can only remove a vector if it's a linear combination of all the other vectors. So let's see what happens. Right, so observe that we can take x squared plus 1 and write it as a linear combination of all the other remaining vectors in S. Okay, so what I'm going to do is I'm going to remove x squared plus 1 from S. Okay, so what I'm going to do is I'm going to create a new set, and I'm going to call, I'm going to basically take the set 1 minus x plus x squared, 1, and x plus x squared, and that's going to be my new set. And I already have the required number of vectors in S prime. There are 3 vectors and the dimension is 3, so all I need to do is check that S prime is linearly independent, because if it's linearly independent it will automatically be a spanning set as well. Okay, so let's take scalars k1, k2, k3 such that that linear combination holds there with the 0 vector on the right hand side, and then again we're going to solve and get the following. So we get that, and then from there we have that, okay, and then from that we have right, so K1, K2, and K3 are all zeros. So what's the moral of the story? This set S prime is linearly independent, and therefore S prime is a basis. Okay, let's look at the second one. There we've got the set 1, 2, 3, 4, 5, 6. Right, so let's look at this problem from a nice perspective. So you take your set S, and we want to form a basis. So what's the dimension of R3? It's 3. So it means that any basis is going to require 3 vectors. Now, unfortunately, S has only got 2, so we need to put in a vector into S. Now, we know what we need to do is we need to find the span of S. Okay, so we need to find all vectors A, B, and C such that A, B, C is a linear combination of the 2 vectors 1, 2, 3, and 4, 5, 6. Okay, so right, so we have to set up a linear system. So look at this linear system here. Right, so we want to find all vectors that are linear combinations of those 2 vectors. So we set up that linear system, and it gives me a matrix, and we know how to do that. The system of equations will A will be k1, 1, plus 4k2. B will be 2k1 plus 5k2, and C will be 3k1 plus 6k2. And then translating that, unknowns, the unknowns are k1 and k2. So we can set up a system with 2 unknowns and 3 equations, and we can compose that little matrix there and then use Gaussian elimination. I want to know, when is this system consistent? When is it not inconsistent? And it's inconsistent. The last row will give me a clue. It will be inconsistent. Well, it will be consistent if this expression is equal to 0. So all I do to pick a vector outside of the span of S is just pick a vector that will make the system inconsistent. And I do that by simply picking this vector here, where that is my value for A, that is my value for B, and that's my value for C. Okay, so if you make A1, B and C are both 0, then this last row is going to be a problem. It's going to be inconsistent. So picking the vector 1, 0, 0 is outside of the span it's outside of the span, and you can go and verify that that is a linearly independent set. And by the plus-minus theorem, if you have a linearly independent set and you have a vector that lies outside of the span of that linearly independent set, then I can throw that vector in, that vector that lies outside of the span, which is this one, I can throw it back into the set to form this set here, and that set will be linearly independent. So now I've got a set of 3 vectors that's linearly independent, and in a finite dimensional vector space I only need to check one of the 2 properties. So it being linearly independent is enough. Okay. All right, let's look at the third one. It's very similar to the second one. There you asked to use those 2 vectors to construct a basis for M22. M22 being all the 2 by 2 matrices. Okay, so how do we do this? We need to find a vector. We need to first see what the span of S looks like, and then we're going to pick a vector outside of the span of S and add it to S. Right, so we take S and we find the span of S. So if we pick a vector, and let's call that vector A, B, C, D. And now we say that this vector is in the span of S, meaning that it is a linear combination of the other 2 matrices. Okay, and basically we set up a system of equations, and you're going to get 4 equations with 2 unknowns, and you're going to set up your matrix, which is going to be this matrix here, and then again you're going to use Gaussian elimination, and a Gaussian will give you this matrix here. Okay, so now this gives me a clue as to what vector I need to pick so that it is outside of the span of S. So you need to pick values for A, B, C, and D. And a value that can work is we can take the matrix where we pick A as 1, we pick B as 0, we pick C as 0, and we pick D as 0. And that will make this last row inconsistent row, and therefore this vector is definitely not in the span. It's not in the span. It's not in the span of S. Right. Now, just a side note, you can also check that the 2 vectors in S, which are these 2 matrices here, you can also show that they are linearly independent. So by composing this equation, you can see that 0k1 plus k2 is equal to 0. So k2 is 0, and you can also see that k1 times 0k2 is equal to 0, so k2 is 0. So that's a linearly independent set. So the plus-minus theorem says the following. The plus-minus theorem says that if you have a vector outside of the span of a linearly independent set S, then I can throw that vector into the set S and I'm still going to have a linearly independent set. So this is a linearly independent set. Now, what is the dimension of M22? The dimension of M22 is 4. So I'm still short one vector. So I need to take this linearly independent set, the new linearly independent set, and I need to further extend it. Alright, so there's my new set S prime. It's got 3 vectors. It's linearly independent. Now I need to go through the process again. I need to pick another vector that's outside of the span of this set. Don't have to check linear independence. I know it's linear independent by the plus-minus theorem. So let's determine the span of S prime. So now you pick a 2 by 2 matrix. Again, you take the 2 by 2 matrix A, B, C, D, and see what needs to happen for this to be in the span of S prime. Okay, so you're going to set up a system of equations. How many unknowns is this equation going to have? It's going to have 3 unknowns. What needs to hold for A, B, C, D to be in the span of S prime? We need to find K1, K2, and K3 such that that matrix equation holds. Okay, and for this to hold, we have a system of linear equations which got 3 unknowns. K1 is going to be an unknown, K2 and K3. And you're going to have how many equations? You're going to have 4 equations. All right, from there we get the matrix, given matrix. And again, I'm just going to quickly show that. So the first row of this matrix corresponds to that entry there. The second row corresponds to that entry there. Okay, the third row corresponds to that entry there. Okay, and the last row corresponds to that entry there. Okay. All right. All right. So we take our matrix, this one here, and we use Gaussian elimination. Take the first row and add it to the last row, and we get the new matrix there. And now what we're going to do is we're going to take -4 the third row and add that to the last row and get. Alright, and then we're going to take of that matrix, we're going to take twice the third row and we're going to add it to the second row and get. And then that we're going to take minus the last row and add it to the first row. Okay, and we're going to get. Okay, and then we're going to take the second row, multiply it with -1/2, and add that to the first row. Okay, and we get, right, so we get our final matrix. Now look at this. The first row gives me a clue as to what I need to choose for the values B, D, and C. Now this system is inconsistent, or it is consistent when this expression here is equal to 0. So to pick a vector that's outside of the span of my new set, we just need to make the system inconsistent. All right, so we can pick A as 0. We can pick B as 0. We can pick D as 0. And we can pick C as 1. And if I plug those values in there, we see that it's going to become an inconsistent linear system. So in that case, this vector here, A, B, C, D, is definitely not in the span of my vector set, my original vector set S union with that other matrix that I chose in the beginning. Alright, so by the plus minus theorem we can throw this vector into my set, and that is going to be linearly independent. Okay, so my basis is the set S, which is basically the two matrices 1, 2, 0, minus 1 and 0, minus 2, 1, 4. Added to that the two matrices, that one, and that set has got 4 vectors. It's linearly independent, and so it will be a basis. Alright, that brings us to Theorem 6. This theorem says if W is a subspace of a finite dimensional vector space, then number 1, W is finite dimensional. Number 2, the dimension of W is less than or equal to the dimension of V, and the only way that the set V and W can be the same is if their dimensions are the same. So quickly look at the first one. Why is it that if W is a subspace of a finite dimensional vector space, why is it then that the subspace inherits the finite dimensional property from the space V? Alright, so we take a subspace W of V, and we take a basis for V, which has got n vectors, and we said V is finite dimensional. Alright, so we claim the following: no set of fewer than n vectors in W can be linearly independent. Alright, let's prove this. Okay, so we start off by, we take W and we take a set W prime of I vectors, such that I is strictly less than n, and W prime is linearly independent. So let's say we can find a set of fewer than n vectors that is linearly independent. And we make sure that we choose I as large as possible. Right, okay. So what we do now is we assume the following. Now, if it happens that the smaller set W spans the capital W, then W prime, if it happens that the span of W prime is W, then W prime is a basis of W. And that's going to mean that W is finite dimensional because W prime has got I vectors in it, and I is strictly less than n. And remember, we said W prime is linearly independent, and if it spans W, then we are done. So we may assume that the span of W prime is not W. Alright, so we know that because it doesn't span it, there must be a vector in W, call it W, such that W is not in the span of W prime. Okay, so what does that mean? Right, so by the plus-minus theorem, we can go and add W to W prime. Okay, and that is going to be a linearly independent set. Now, if this I is less than or equal to n minus 2, then this set here is going to have fewer than n vectors. Alright, so it's got fewer than n elements. and also W added to W prime is going to be larger than W prime, and it's contradiction. Remember, we chose W prime to be the largest linearly independent set in the subspace W. But now I've found an even larger set, which is the set W prime added to that W. So you're going to have that set is still linearly independent, and it is got fewer than n vectors, and it is going to be larger than I, and that's going to contradict the way that we chose our original set W prime. Okay, so we may assume that I is not less than or equal to n minus 2. It is equal to n minus 1. So therefore, this set here is going to have n vectors in it. And it's going to be a linearly independent set. Okay, so what does that mean? What that means is, it follows that the set W prime union W, we know it is linearly independent, it's got n elements, and we know that any set of vectors that's got n elements in a vector space that's n-dimensional, we know that that set must immediately, if it's linearly independent, must be a basis for the whole of V. So this set here is a basis for V. And so it must also be a basis for W, because this is contained in W, and therefore it spans W. So that is going to imply that W is finite dimensional. Right, so we proved our claim, and our claim was that the set W, if you take any a subset of W of fewer than n vectors, then that chosen subset can never be linearly independent. Okay, so let's just prove our statement, which is that W is finite dimensional, and the dimension of W is less than or equal to the dimension of V. All right, so now if W is only the zero vector, then we know by definition the dimension of W is 0. And therefore W has finite dimension. So W is finite dimensional. And obviously the dimension of W is less than or equal to the dimension of V. So we may assume that W is not only the zero vector, so W has a non-zero vector. Right, so W has a non-zero vector. Let's call that vector, let's call it W, okay? Alright, so what happens if the dimension of V is at least 2? That means that N is at least 2, and we contradict our claim. Now, why are we contradicting our claim? What claim are we contradicting? That's the question. What claim are we contradicting? Alright, remember this claim here. This claim, we said that no set of fewer than n vectors in W can be linearly independent. Okay? Now, if we take the non-zero vector W and we make that our set in capital W, now a set that contains one non-zero vector is obviously linearly independent, and therefore we contradict our claim by just taking our set as this W, because that's a linearly independent set that's got fewer than n vectors that's linearly independent. So we contradict this claim clearly. So therefore, what can we then say? Right, so we can then say that n is 1. Well, we can look at the case where n is equal to 1, and if the case of n, in the case of n equals 1, we have that the basis contains only one vector v, and therefore there's a vector v that spans the whole capital V. And that means that every vector in V is a linear combination of, or is a scalar multiple of this vector. It's a scalar multiple of that vector. Right, so what does it mean? We know that because the vector V spans the whole space capital V, we know that every vector in W can be written as a scalar multiple of the vector V, right? So we can basically say there exists a scalar K such that we can write W as a scalar multiple of the vector V, and because W is a non-zero vector, it means the scalar must be non-zero, so we can easily see that V must be a scalar multiple of W. So therefore, this is going to imply that V must be in the subspace W, because for V to be in the subspace W, it must be a linear combination of well, if a vector is a scalar multiple, in this case V, if V is a scalar multiple of a vector in capital W, then that vector is going to be in capital W, because capital W is closed under scalar multiplication. So hence the span of V, because V is in capital W, the span of V is going to be the whole of capital W, because V spans the whole vector space V, right? Okay, so it's going to mean that W is finite dimensional, and the dimension of W is less than or equal to the dimension of V. Okay, so the dimension of W is going to be at most 1. Alright, and if n is 0, in other words the dimension of V is 0, then obviously the dimension of W will be the same as the dimension of V. Because if V is the 0 vector, then W will be the 0 vector as well. Alright, so the other two properties, I can refer you to the textbook to go and look at the derivation of that. Alright, so the next section is somewhat of a tutorial, a few extra exercises. I'm going to leave exercise 1 for you guys to do and exercise 3. I quickly just want to look at exercise 2. Here they ask me to characterize whether a given set is a basis for a finite dimensional space using determinants. Okay, so depending on what the vectors look like, I want you guys to go and think back again to all the theorems we've looked at. In a finite dimensional vector space, all I need to check for a set to be a basis is whether that set is linearly independent or whether that set spans V. So essentially, all I need to actually check is the linearly independence. So if I can establish when will linearly independence, when that property will hold, then I will be able to answer the question. Alright, so let's take finite dimensional vector space V, and let's take an arbitrary set of n vectors. Right, so there we've got our set. Okay, and when is that set a basis? It's a basis if and only if what happens? If and only if S is linearly independent. That's all I need to check, because it's finite dimensional. Alright, and when is S linearly independent? It's linearly independent if that holds. In other words, setting up that equation only has the trivial solution. Alright, and the only way that can happen is if the following holds. The system L generated by this equation, the one we talked about just now, this one here, that one there, has the trivial solution. This is the linear system L. So remember, from here you're going to get a linear system of equations. you're going to set up a linear system within unknowns and a certain number of equations, and you're going to solve that system. And if that system has a trivial solution, then it's linearly independent. And what needs to happen for that to be true? Right, we need the following. Right, what needs to happen then is this. The only way that can happen is if the matrix equation generated by L, so if you're going to take the system of linear equations L, and you set up the matrix equation generated by that linear system, which is this matrix equation here, okay, as the trivial solution. And the only way that can have the trivial solution is if A is invertible. All right, and the only way that can happen is if the determinant of A is not equal to 0. So therefore, A is invertible. All right, so that's your characterization. Setting up your matrix equation from your linear system. The linear system that you get from this equation here, the coefficient matrix A needs to be invertible. Then this system here will have the trivial solution only, and that only happens when the determinant of A is not 0.